Good afternoon, everyone. My name is Hanfei Dong from Hanyang University in Korea, and my advisor is Professor Simon Song. In this presentation, I'm going to talk about direct measurement of turbulent kinetic energy on CrossJet flow using magnetic resonance velocimetry. First, I will give you a brief introduction to MRV. MRV is a flow visualization technique that uses a conventional MRI scanner. It measures in a 3D region and is a non-invasive technology that doesn't require tracing particles. Because MRV uses magnetic field signals for measurement, it's suitable for opaque and complex flow environment. And MRV can measure a wide range of characteristics, including velocity, TKE, temperature, concentration, and renal stress tensor. And it was primarily used in the medical field, particularly in applications like the flow inside the heart and arteries. Currently, it is also widely used in various engineering flow fields, such as the flow inside the refrigerator machine room. This paper includes detailed explanations of the MRV text section design, experimental setup, and MRI scan parameters we used. If you are interested in MRV applications in engineering flow, this paper will be helpful. Next, I would like to introduce the research background. Do you know about MRV Challenge 1 and 2? MRV Challenge is an international collaboration aimed at comparing and benchmarking the performance of MRV techniques across various research groups. So far, MRV Challenge 1 and 2 have been completed. MRV Challenge 1 focuses on mean velocity measurement in a highly turbulent steady-state U-band flow, while MRV Challenge 2 focuses on the mean velocity measurement in a positive CrossJet flow. And you can find detailed information in the relevant papers. The main finding of MRV Challenge 1 and 2 is that different research groups use different MRI scanner and different MRI scan sequence. All obtained mean velocity results that show good consistency, demonstrating the reliability and good accessibility of MRV technique. Currently, there is no fully disclosed information that MRV Challenge 3 is in progress. The scope of MRV Challenge 3, in addition to mean velocity measurements, primarily focus on the measurement of temperature, concentration, and TKE, using the same geometry as MRV Challenge 2 but in a steady state. This geometry is chosen because it's complex enough to induce turbulence and generate various complex flow features. And the difference in concentration and temperature between the injection and main flow creates strong mixing phenomenon. So this presentation will focus on the TKE measurement. And the primary objective of this research is to measure and analyze 3D TKE and flow characteristics of CrossJet flow using MRV. So first, we measure the stream-wise turbulence intensity in a circular pipe using MRV and compared it to DNS data. And then we conducted measurement of 3D mean velocity and TKE of CrossJet flow using MRV. And finally, we conducted an analysis of signal attenuation ratio and TKE isosurface based on MRV measurements. First, I will explain the principle of turbulence intensity measurement using MRV. As you know, the principle of turbulence intensity measurement using PIV relies on calculating the standard deviation of instantaneous velocity fluctuations as a proportion of the mean velocity. However, MRV measurements are based on the phenomenon of signal loss due to intravoxel phase dispersion when velocity fluctuations occurred in a magnetic field. So by quantifying the signal loss and using this formula, the turbulence intensity can be directly calculated. The results are shown in this figure. The streamwise turbulence intensity measured using MRV were compared with the DNS data using inner scaling. The turbulence intensity is usually applied by considering the peak value as important. So as shown in this figure, in the case of Reynolds number of 11,700, there is an approximate relative error of 0.4% can be observed between the MRV and DS data. And in the case of Reynolds number of 37,700, a relative error of 4.6% can be observed. This indicates that MRV has good accuracy in measuring the peak of turbulence intensity and can effectively capture the main characteristics of turbulence intensity. Additionally, KV is flow sensitivity. In this formula, calculated as pi divided by bank, and bank is the parameter that we directly set before conducting the MRV experiments. A lower relative error can be achieved between MRV and dense data at the center region of the circular pipe by setting a higher bank value. Therefore, we also use the multi-bank method to measure streamwise turbulence intensity, and the results are shown in this figure. In the area near the wall, where the velocity values are relatively low, the results obtained with lower bank value show good consistency with the DNF data. Conversely, in the area closer to the center where the velocity is higher, the results obtained with higher bank value show good consistency with the DNS data. This indicates that the multi-bank method can be effectively used to improve TK estimation by combining the best result from each bank measurement. And we hypothesize that using bank value proportional to the velocity in specific regions results in accurate turbulence intensity measurement. The following is the schematic representation of mean velocity and TK quantification using MRV. The MRV signal consists of phase and signal magnitude. So the mean velocity measurement based on the phase difference, while the turbulence intensity measurement based on the signal magnitude. So by using the difference of these two signals known as signal rules, the turbulence intensity in X, Y, and Z directions can be directly calculated. And finally, the TK data can be obtained by using this formula. So from now on, I will explain the experimental setup for the CrossJet flow. As you can see in this figure, we have a closed-loop circuit including pumps, flow meters, reservoir, and flow control and data acquisition instruments. This experiment used the same geometry as shown in MRV Challenge 2, and 6 cubical elements are positioned at the wall and channel center, and there is a main flow from left to right and an injection flow from bottom to top. And to ensure uniformity of the main flow at the inlet, the flow conditioners and boundary layer trap were installed. Next, I will explain the flow conditions and MRV scan parameters. The working fluid used is copper sulfate aqueous solution. The main flow operates at a Reynolds number of 15,000 with a flow rate of 22.2 rpm, while the flow rate of injection flow is 1 rpm. The MRV experiments were conducted using the 3T human MRI at Korean Basic Science Institute Ochang campus. The FOV were 256, 96, 96 mm with a 0.5 mm isotropic spatial resolution. And for mean velocity measurement, the bank value for 3 flow directions were set to 110, 110, and 90 respectively. The data were obtained by applying a signal average of 6 with 2 flow-on cases and 1 flow-off case used to calculate the averages. And for TK measurement, the bank value for 3 directions were set to 30, 30, and 25 respectively. The data was obtained by applying a signal average of 12 with 10 flow-on cases used to calculate the average. From now on, I will talk about the results of flow visualization. First, I will show you the cross-section result of mean velocity and TKE at Z-plane. For mean velocity data, the arrow indicates the in-plane velocity, while the contour indicates the out-of-plane velocity. So as shown in this video, a large TKE is generated due to the boundary layer trip and the boundary effects near the wall. And then we can observe that due to the effect of mixing phenomenon between main flow and injection flow, and 6 cubical elements positioned at the wall and channel center, a large TKE is generated. Next is the result at X-plane. From this result, we can more clearly observe the TKE patterns generated near the wall from the boundary layer trip and the cubical elements. And next is the result at Y-plane. So from this perspective, we can more clearly observe the TKE distribution generated when injection flow merges with the main flow. And next, I will show you the result of isosurface of normalized velocity. The green isosurface represents regions where the velocity is 1.2 times the average bulk velocity at the inlet. We can see that many isosurfaces generated at the downstream of the boundary layer trip. Then the cubical elements positioned at the wall and channel center reduce the flow area and generate complex fluid disturbance, leading to the generation of a large number of velocity isosurfaces in the middle and downstream regions. And the red isosurface represents regions where the velocity is 1.5 times the in-plane velocity. Compared to the green isosurface result, the higher velocity region is more localized around the first cube and in the area where strong interactions occur between the main flow and injection flow, resulting in many isosurfaces. And we can see that this effect diminished quickly downstream. And next is the analysis of signal attenuation ratio in the streamwise direction. Previous studies have reported that signal attenuation ratio determines precision and accuracy of the TK estimation. The optimum sensitivity can be obtained by using a bank value that results in SKV divided by F0 of 0.6. So as shown in this figure, in the region where there is less than 50 millimeter, the signal attenuation ratio falls between 0.7 and 0.9, resulting in poor sensitivity for TK estimation. This is because of low turbulence level in the inlet region where signal loss has not occurred sufficiently. So in this area, by using a lower bank value, the signal attenuation ratio can be reduced to about 0.6 to achieve good sensitivity in TK estimation. In the region where there is larger than 50 millimeters, the signal attenuation ratio is around 0.6, indicate good sensitivity in TK estimation at this region. This demonstrates that the chosen bank value enable accurate TK measurement in the CrossJet flow region. And the momentum distortion parameter is the dimensionless parameter used to quantify the distortion in the velocity profile and is defined as follows. It is calculated based on the difference between the actual momentum distribution and that of a uniform flow. So as you can see in this figure, the similar trends can be observed between the momentum distortion parameter and the average TKE at the same locations due to their close relationship with the complexity of the flow and the turbulence. Even in the poor sensitivity area of TKE measurement, we can still see that the momentum distortion parameter and the average TKE maintain this relationship well. And this is the TKE isosurface result. The left side shows the isosurface result of MRV tech section with a value of 20 joules per cubic meter. As you can see, a large TKE is generated in the downstream of the injection flow inlet, cubical elements, and boundary layer trip. The right side shows the TKE isosurface result of CrossJet flow region. with a range of values from 10 to 40 joules per cubic meter. And we can clearly observe the variation in TK exosurface ranging from 10 to 40, with the maximum TK value occurred downstream of the first cubic element after the injection flow inlet. So in this study, we successfully visualized the 3D mean velocity and TK of CrossJet flow using MRV, demonstrating the capability of MRV to visualize the flow in such complex and opaque flow environment. In the future work, we will try the multi-bank measurements by combining the best result from each bank measurement to achieve improved TK estimation. Thank you.